the universe's most ruthless, most mysterious predators. They are invisible, but their mass can be millions of times greater than our sun. They devour even light, and once you are caught, escape is impossible. They are black holes. In this video, we explore the secrets of these cosmic monsters. How do they really form? What's inside them? And what happens if you cross a black hole's event horizon? Get ready. We're taking a journey to the strangest and most terrifying corners of the universe. Billions of stars light up the vast expanse of our universe, forming majestic galaxies that stretch across unimaginable distances. But within these seemingly stable cosmic structures lurk forces of unimaginable power, entities so bizarre and extreme that they defy our everyday understanding of physics. These are the cosmic monsters known as black holes, regions of space-time where gravity is so intense that absolutely nothing, not even light itself, can escape their grasp. For centuries, they existed only in the realm of theoretical physics, the wild and mind-bending predictions of Albert Einstein's theory of general relativity. It was Einstein's revolutionary work, published in 1915, that first laid the mathematical groundwork for the existence of these gravitational singularities. His equations suggested that if enough mass were concentrated into a small enough space, the resulting gravitational field would become infinitely strong, creating a point of no return. This theoretical point of no return, the boundary beyond which nothing can escape a black hole's gravitational pull, is known as the event horizon. It's not a physical barrier, like a wall, but rather a conceptual boundary in space-time, a point where the escape velocity required to overcome gravity exceeds the speed of light. Think of it as a cosmic waterfall. Once you cross the event horizon, you are forever swept inwards, towards the black hole's enigmatic center. The size of a black hole's event horizon is directly proportional to its mass. The more mass a black hole contains, the larger its gravitational influence and its event horizon. A black hole with the mass of our sun would have an event horizon with a radius of about 3 kilometers, a tiny sphere compared to the sun's vast size. However, the most intriguing and terrifying aspect of black holes lies not at the event horizon, but at their very center, a point of infinite density known as the singularity. At the singularity, all the matter that has ever fallen into the black hole is crushed into an infinitely small volume, a point where the laws of physics as we know them break down completely. Our current understanding of gravity, general relativity, fails to provide a complete picture of what happens at the singularity. It's a realm where space and time themselves become distorted beyond comprehension. The concept of a singularity is one of the biggest challenges in modern physics, a place where quantum mechanics and general relativity, our two fundamental theories of the universe, clash dramatically. So, how do these cosmic monsters actually form? The most common way involves the death of massive stars, stars that are significantly larger than our own sun. Throughout their lives, these giant stars burn brightly, fusing hydrogen into helium in their cores, generating immense outward pressure that counteracts the inward pull of gravity. But when these stars exhaust their nuclear fuel, the outward pressure fades, and gravity takes over, causing the star's core to collapse violently inwards. For stars up to a certain mass, about 3 times the mass of our sun, this collapse is halted by the formation of a super-dense neutron star. However, for stars more massive than this critical limit, gravity overwhelms even the incredible density of neutron matter, and the collapse continues relentlessly, forming a black hole. The outer layers of the dying star are often expelled in a spectacular supernova explosion, a final, brilliant burst of light and energy that can outshine an entire galaxy for a brief period. Left behind is the incredibly dense core, now a black hole, a silent and invisible gravitational well in the fabric of space-time. But black holes don't just form from dying stars. Supermassive black holes, millions or even billions of times the mass of our sun, reside at the centers of most large galaxies, including our own Milky Way. The formation of these colossal black holes is still an active area of research, but one leading theory suggests they grew over billions of years by swallowing vast amounts of gas, dust, and even other stars and black holes. Another possibility is that they formed from the direct collapse of enormous primordial gas clouds in the early universe, bypassing the need for individual massive stars. Regardless of their origin, these supermassive black holes exert a tremendous gravitational influence on their host galaxies, shaping their structure and influencing the orbits of countless stars. Despite their fearsome reputation as cosmic devourers, black holes are not simply giant vacuum cleaners, sucking up everything around them. An object has to come relatively close to a black hole's event horizon to be pulled in. At a safe distance, the gravity of a black hole is no different from that of any other object with the same mass. Our solar system, for example, would continue to orbit a black hole with the mass of the Sun in exactly the same way it orbits the Sun now, just in perpetual darkness. However, the environment near a black hole can be extremely violent. Gas and dust falling towards the event horizon form a swirling disk known as an accretion disk. As material in the accretion disk spirals inwards at incredible speeds, friction generates immense heat, causing the disk to glow intensely across the electromagnetic spectrum, emitting powerful X-rays and gamma rays. These energetic emissions are some of the brightest objects in the universe and are our primary way of indirectly detecting the presence of black holes. But what happens to something that actually crosses the event horizon of a black hole? According to our current understanding, the fate is rather grim. An object falling into a black hole would experience a phenomenon known as spaghettification. The immense difference in gravitational pull between the near and far ends of the object would stretch it out dramatically, like a strand of spaghetti. For smaller, stellar mass black holes, this stretching force would be so intense that the object would be ripped apart long before it even reached the singularity. However, for supermassive black holes, with their much larger event horizons and gentler tidal forces at the horizon, an object might remain intact for a bit longer as it plunges inwards. But ultimately, everything that crosses the event horizon is destined to be crushed into the singularity, adding to the black hole's ever-increasing mass. One of the most mind-bending predictions about black holes is the possibility of time dilation. According to Einstein's theory, gravity warps space-time, and the stronger the gravity, the slower time passes relative to someone far away. For an observer watching an object fall towards a black hole, the object would appear to slow down as it approached the event horizon, its time stretching out infinitely. The object would seem to freeze at the edge, its light becoming increasingly redshifted until it eventually faded from view. However, for the object falling in, time would continue to pass normally until it was ripped apart or reached the singularity. This creates a bizarre asymmetry in the perception of time. Black holes are not just theoretical curiosities. They play a crucial role in the evolution of galaxies. The supermassive black holes at galactic centers are thought to regulate star formation and influence the distribution of matter within their host galaxies. Active galactic nuclei, powered by supermassive black holes feeding on vast amounts of material, can emit tremendous jets of energy and particles that extend for millions of light-years into intergalactic space, profoundly impacting their surroundings. The study of black holes has led to some of the most profound insights in modern physics, pushing the boundaries of our understanding of gravity, space-time, and the ultimate fate of matter and energy. And while they remain shrouded in mystery, with the singularity still beyond our complete comprehension, black holes continue to captivate our imagination, serving as a constant reminder of the universe's vastness and its astonishing extremes. So, the next time you gaze up at the night sky, remember that hidden within the seemingly tranquil darkness lurk these cosmic monsters, silently shaping the universe on the grandest of scales. They are a testament to the power of gravity, the strangeness of space-time, and the endless wonders that await us in the depths of the cosmos. What other cosmic mysteries ignite your curiosity? Share your thoughts in the comments below, and let's continue our exploration of the unbelievable universe together.